This is all part of work with Canucks at Marcin Zawicki and Kay Bremer. All right, so I'm going to give you the overview of what I'm going to be talking about today. First, I'm going to talk about a general overview of what is grism data if you're unfamiliar with it, and then some of the work that I've done in the past with grism data. Then I'm going to talk about the spatially resolved side of grism, some of the work that's been done there, and how we are going to go ahead and simulate some grism data. And then finally, I'll tell you about some of the results from actually doing spatially resolved SED fitting using grism data. This is all extremely new work. I mean, some of this analysis was done yesterday. So yeah, very, very new, but really interesting to see what we've been able to get done. So first is working with grism data. And grism data is just spectroscopy, essentially, right? If you're unfamiliar with it, it would be a good time to sort of get familiar, at least a little bit with it, because you're going to start seeing grism data more and more. Basically, every big space telescope is going to have grism. JWST already has multiple grisms on the different instruments. Hubble has grism capabilities. Euclid will have grism. Roman Space Telescope will have grism. Even the Canadian-led Castor is planned to have grism. So this is a data set that you will see coming up more and more often. And here is some grism data. As you can see, on the left is a direct image from Hubble, and on the right is the grismed image from Hubble. And so, you know, slitless spectroscopy, there's no slits, you just expose and disperse everything. And I think my favorite thing I've heard someone say about grism data is the best part about grism data is you get spectra for everything in the field. And the worst part about grism data is you get spectra for everything in the field. It's a mess, right? You can see there's spectra falling on top of each other. There's these 0th order dispersions you can see here, as well as from really bright objects. There's the other orders that you have to worry about. You'll notice that these objects have been shifted. That's because when you do this, you're going to, objects that may not be in the field are going to get dispersed onto it. Yeah, it's a mess. It's very contaminated, very difficult to work with. But luckily, there's a lot of smart people out there, and they've developed ways to deal with all this contamination, which has made my life a lot easier. The way that we deal with the contamination is to disperse the objects at different angles. For Hubble, we did this by rotating the whole instrument, the whole telescope, and you can disperse the light at different angles. For NIRISS, the light will be dispersed orthogonally, right? So we'll have light dispersed in one way and then 90 degrees, and that's how we'll get the different orients. So here's an example of why this is important. Here is the object that we're interested in. And here's a nearby source. And dispersed at this angle, the two spectra lie right on top of each other. And there's basically nothing you can do to remove that contaminating source here if you only had the one orientation. But as you rotate Hubble, you can disperse the object slightly separated and then even more, right? And it's even more separated. By doing so, you can better model the contaminating source and remove it. And so with Hubble, again, you know, we did this by rotating the whole instrument. With NIRISS, we'll have the orthogonal angles to help with the contamination. The other big concern we have to deal with grism data is something called morphological broadening or self-contamination. So when the grism creates the spectra, what you're sort of doing is stamping down images of the galaxy at each of the wavelengths. This is really nice because it will give you the spatial information about the galaxy, but it can cause some issues. As a result, when you look at the 1D spectra, you get the highest resolution when you're looking at really nice, compact, spheroidal galaxies. But when you look at more extended galaxies, what happens, again, because you're stamping down the image of the galaxy, is that light from one wavelength will bleed on over into the other, broadening the features and smoothing things over. Here, what you're seeing is I've given both of these galaxies, I simulated them with the exact same SED, and this is what it would look like for each of these galaxies. So you can see there's a big difference. And so to deal with this morphological broadening, the self-contamination, I use a forward modeling technique. To do that, I use the software package Grizzly, which is basically, does anything you want to do with grism data, you can turn to Grizzly and it'll do it for you. And I use its code to generate the forward modeled grism spectra. The way it works is you take your SED. In this case, I'm using FSPS. Take the morphology of the galaxy at the right orientation. You hand that over to Grizzly and it can produce this 2D spectra for you. And if you wanted to, you can extract this down to 1D, which is some of the work I'm about to show you that I've done with 1D grism spectra. So here I have some 1D grism spectra. And here in red is a best fit model. So what I've done, the work I've done is focused mostly on massive quiescent galaxies at redshifts between 1 to 2. And in the paper I'm showing you right here, I looked at things like metallicity and age. And doing so, I was able to get a decently large sample of massive quiescent galaxies between redshifts 1 and 2 and measure the mass stellar metallicity relationship. And what we found was that this relationship, at least in this mass range and up to these redshifts, does not evolve as a function of redshift. Massive quiescent galaxies in this mass range, once they quench, they have about a solar metallicity. Moving forward from that work, I then developed methods to fit not only grism spectra, but multiple grism spectra. This is Hubble data, and this is G102, G141 grism spectra from Hubble, plus photometry to do these SED fits all simultaneously and able to fit, star-forming galaxies, Green Valley, all the way up to quiescent, and produce some really, really nice SED fits. In addition, I used some really flexible star formation histories, and that work, we studied the relationship between when a galaxy formed and how compact it was. And on the y-axis here, you see Z50. This is the redshift where the galaxy formed half its mass. The y-axis is sigma 1. This is essentially how compact the galaxy is, where here is more compact. And what we found was that the more compact a galaxy was, the more likely it was to have formed early on. And we've been able to do some really interesting things with 1D grism spectra, but it's limited, right? And specifically because with grism, you get that spatial information, but when you go to 1D, you lose it all. So what has been done using spatially resolved grism data? Well, the work that's mostly been done has been done using emission line maps. So an emission line map, here we have a galaxy, right? We have old red stars underneath, and then the star forming spiral on top. As you disperse that, you get this continuum from the old stars. And again, because you're stamping down an image of the galaxy, you get an image of the galaxy in the light of that specific emission line. So whatever emission line this is, you will get the spatial distribution of that emission line throughout the galaxy, right? And the way we do emission line maps, essentially, this is a very simplified version of this, is if we can fit that continuum, we can remove it, leaving only the light from the emission line that you can see here. Some of the work that's been done, I'm going to highlight some of the work from some collaborators. This is work from Raymond Simons at SCSCI in the CLEAR collaboration. And what he did, he took emission line maps for O2, H beta, O3, and from those, got gas phase metallicity maps for these galaxies. Here's some of these gas phase metallicity maps here. Here's two different examples. Here's some more. Here's the direct image of the galaxy, and here are the metallicity maps. And from these, you can do things like measure metallicity gradients, as you can see here. Some other work that's been done with emission line maps is from another collaborator, Jadeline Matharu, where she was looking at the direct images, which you see here, the F105W, and the H alpha maps, which you can see here. And by comparing the two, right, you're essentially comparing the continuum to the star forming regions of the galaxies. You can measure morphology, do a lot of interesting stuff there. And you can in fact see some structure, which is really cool, in these H alpha maps. So yeah, a lot of interesting work has been done with emission line maps and spatially resolved work. But in the realm of SED fitting, we haven't yet been able to take advantage of this. So to take advantage of this, I turned to some spatially resolved SED fitting that was done in photometry. So this is some work that was done by Bobby Sorba, a former student of Marcin Zawicki. What Bobby did was he used photometry to fit spatially resolved some galaxies, I believe is in the UDF. And what you see here, so this is the galaxy that he fit. Well, he fit multiple galaxies. This is the galaxy I'm going to focus on because this is the galaxy I'm going to do. I'm going to model with NIRISS. But you get all these property maps, things like mass, star formation rate, and these SED fits. I can use these properties to generate SEDs and use those to generate spatially resolved, properly spatially resolved grism spectra. Because if I were to do this, you know, when I showed you the forward modeling slide, the way I do this is you take one SED and you take the galaxy and then you create the image. We don't want that, right? We want there to be spatial variation. And we can use these maps to actually do that. So here are some more maps, and here's another false color image. That's that same galaxy. And I picked this galaxy specifically because it's pretty complicated. For instance, there's two cores here. There's some star forming regions that you can see. You can in fact see the two cores in the mass maps, the star forming regions in the specific star formation rate maps. And you can see the difference in the ages. And this is because this is likely emerging system, right? You have an old galaxy. This is why you have two cores. You have an old galaxy merging with a younger galaxy. And so trying to fit this with a single SED, I mean, you're not going to get a good fit. So this is the perfect candidate to do this spatially resolved work. And in fact, here are the mock NIRISS grism images. One thing I want to add is this galaxy that Bobby looked at was at Redshift 1, but NIRISS works really nicely with Redshift 2 galaxies. So I went ahead and adjusted some of the properties to work better for Redshift 2. So this is actually a Redshift 2 SED. But I'll show you some of the features that we see here. So the most prominent one you see here is H alpha. This right here, again, remember, you're stamping down an image of the galaxy. So this is an image of the galaxy in H alpha with continuum behind it. Here's the galaxy again, if you want to sort of center yourself. In F150, we see O3, and the slight thing over here is H beta. And even more dim here in F115W is O2. So you can see several of the features that we see. Now, this next slide is just for fun, but I just wanted to see what the grism looks like in 3D. So here's some 3D images of the simulated grism data, but you can see some really cool things pop up. I mean, first of all, you see the H alpha, the distribution of H alpha within this galaxy, right? That's really cool. Here's the 3D version of this galaxy. It's just, you know, Z-axis is just flux. This little ridge here isn't really interesting because you actually do see that in the grism data. By eye, I don't remember seeing that, but yeah, you see the O3, the H beta. This one's just for fun. I just wanted to see what this would look like. Okay, but let's say you say, okay, I still want to do this in 1D. I don't want to do this in 2D. All right, well, here's what the 1D spectra for this galaxy would look like. If you're familiar with galaxy spectra in the optical range, you may be looking at this and saying, this makes no sense. And you're right. For instance, these two things right here, they're both H alpha. These two things here are both O3. This is O2, and no, this isn't at the wrong redshift. This is right. This is the right redshift. But remember, things are spatially distributed. So you see, okay, H alpha plus N2. That's an important detail. But H alpha N2 is right here near 2 micron. So it's right around here. But this big star forming region is off center, of course. So this is why we see this flux over here. Same thing for H beta and all the other emission lines, in fact. And this is a big reason that you need to do forward modeling if you want to do SED fitting of this galaxy of grism data. I've seen, some approaches where they just, they change the resolution of the model spectra. That can work if you have a really nice compact elliptical galaxy. But if you have a galaxy with structure, a galaxy with star forming regions, it's not going to work. I kind of do think you could do some analysis of this galaxy in 1D. I haven't tried it, but I think you can. You absolutely have to do forward modeling. Here's this one. And in fact, here's the orthogonal angle. This one's even more complicated because, so going back, remember, this is H alpha, right? But the light's about to be dispersed orthogonally. So this whole thing here is H alpha emission over this grism spectra. The same thing for O2, O3, H beta. Yeah, it's contaminating, like the self-contamination I was talking about, is contaminating the entire spectra. And so you're going to lose a lot of information trying to do this in 1D, or even just trying to do this with one SED. This is why we want to do the spatially resolved SED fitting. So let's go ahead and talk about how I go about doing just that. So, I'll go back here. The way that these were generated, remember when I talked about the forward modeling, right? You take the image of the galaxy, you take the SED and it forward models it. The way that this was generated was you take each pixel of the galaxy, you take the SED and you forward model it. So this is built pixel by pixel. This galaxy, I'm guessing, had around 3,000 pixels. And the thing is, when we do spatially resolved fitting in the grism, see, when you do that with photometry, you can treat each pixel as its own spectra. So you can just fit each one independently, which is really nice. And you can, fit pretty quickly. You can't do that with the grism because when you generate the SED, it's all self-contaminated. You have to fit everything simultaneously. So if you were to do a pixel by pixel fit for this galaxy in particular with 3,000 pixels, then you would need to simultaneously fit 3,000 times however many parameters you have for your SED. And right now, for SED fitting, I use 4 to generate the SEDs. So it's 3,000 times 4, all fit simultaneously. I don't know if there's enough time to do all that kind of fitting. So especially for a galaxy this big, for a galaxy that's really small, we may be able to do pixel by pixel fitting. That's something we will need to address in the future. So the way we're going to do this is instead to break this galaxy into different regions, essentially resegment the galaxy. We're going to do that using different properties. So again, here's the image of the galaxy. There are some properties we have from our fitting: mass, specific star formation rate, age. And I'm working with a student here at St. Mary's to figure out how are we going to do this. So he's developing methods using machine learning, looking at parameters like color, distance from the center, even derived properties like mass and specific star formation rates. And even though we won't obviously be getting those from JWST, within Canucks, we are equipped to do spatially resolved SED fitting on photometry. So that might have to be the first step, is we do the spatially resolved SED fitting with photometry, generate specific star formation rate and mass maps, and then use those to resegment the galaxy. But this is one way, for instance, to segment the galaxy that my student Lucas has developed, right? And so each different color here is a different region that will be fit for the spatially resolved SED fitting. And we're trying to do this automatically. The way I'm going to show you that I actually did for the fits that I'm going to show you was all done by eye. But remember, because with grism, we're getting spectra for everything in the field. We're not going to be doing this with 1 or 2 galaxies. We're going to be doing this with hundreds of galaxies. So we don't want to have to sit there and do this all by eye. We want to have it done automatically. And Lucas is developing this. In fact, we're at the point in his work where he's going to start giving me segmentation maps using all different combinations of properties, colors, and mass and whatever. And we're going to test those to see what sort of works the best. Here are some additional segmentation maps he's generated with these different galaxies, all the same idea. And it's working out pretty well. At least the segmentation maps look good, but we have to see how well they actually do at fitting the galaxy. The way that I actually did it for this, because again, we're still testing that, is to do it by specific star formation rate. So this is what I segmented the galaxy by, and here's what this looks like. This is not an ideal way to do it. They're pretty messy regions, right? Also, and this will show up when I actually show you the fits. This region here, this beige one, is the lowest specific star formation rate. In fact, here are the distributions of the specific star formation rates for each one of these. And it's essentially these 2 cores plus some of the old part of the galaxy. But ideally, you would separate those 2 cores, right? This core should be separated from this one. I mean, if this is a merging galaxy, it's not even part of the same galaxy. And I really wanted to have updated fits for y'all, but I had fits running yesterday and they just timed out. 30 hours was not enough. This one I'm going to show you ran in like 27 hours. So these do take a long time to run. And I resubmitted the jobs and giving them 50 hours, which should be way more than enough time. But that's actually a consideration we need to take into account here, right? Because we have limited resources. We only have so many hours we can use to fit. And we have to strike this balance between enough regions that we get higher resolution fits, but not enough that we're taking a week to fit a galaxy, and that is something I will work out with Lucas. The two segmentation maps I'm showing you, one is everything. I'm going to show you what it would be like if we just fit this galaxy, how it's been normally done with one SED, and then one here. This is 5 regions, again, separated by specific star formation rate. And here's actually the different regions in the galaxy, right? You have the old and sort of stuff in between, and then you get to the star forming regions of the galaxy. And here's a little GIF of how this actually generates the mock SED, right? Essentially, again, we start off with this chunk of the galaxy, right? We get an SED and we forward model it. And then we pick the next one, same thing. And we just keep doing that until we've built up the entire galaxy. And this is what that would look like. So the first thing I'm going to show you is fitting using one region, right? So we're going to just fit with one region. The top is the the simulated grism images, the NIRISS images, and the bottom are the best fit models using one region. By eye, these look decent, right? You get H alpha, and it looks pretty good. when we look at the residuals, we see obvious structure that's been left behind here. I don't remember whether red's over subtracted and blue is under subtracted. It's something like that. But yeah, obviously, this galaxy has some old cores. It's got an old port, again, it might be two merging galaxies. So there's an old portion, an old galaxy within this. There's a star forming region. So the SED it landed on was just something in between. And so, it can only do so well. Here is the best fit model using the 5 different regions. Again, by eye, this looks good. There are some slight variations, but really this is the big one. Here's the residuals when we look at what it's like with the 5 different regions. It's not perfect. Again, I said that this isn't the ideal way to do this, but this is much, much better than fitting with one region. In fact, I think the biggest thing that gets left behind is one of the cores, which, as I said earlier, we're fitting the 2 cores together, which they really should be separated. And in the newer fits I'm doing, they are separated. But that's really it, except for some of the continuum, here. It does affect, here's a comparison of the fitting everything with one SED as one object, and here it is fitting it spatially resolved, fitting it with 5 different regions. And we are pushing, in fact, to have more. So so those are just the 2D spectra. What about some of the actual properties? So the one I'll show you is star formation history. So to generate the star formation histories for each one of these pixels, I turned to the work that Bobby did. And all I needed was the stellar mass and then the age and tau. So these are delayed tau models that were used to fit. So if you're not familiar with those, it's just a way to parameterize star formation history. And each one of these you see here is a star formation history for each one of the pixels. To get the overall star formation history of the galaxy, I just summed those up, and that's what you see here on the right. This is the overall star formation history in look back time, just so you know. So the galaxy was observed around here. But this is what that would look like here. And again, this is using a delay tau model. To do what I'm using to do to fit the star formation histories is I'm using the star formation histories from dense basis. I'm not using dense basis itself to do the fitting, but I am using its star formation histories. And it's one of these really flexible star formation history codes. Here are some of the star formation histories you can get from it, all different kinds of shapes. The really nice part about dense basis is you need very few parameters to actually fit it. Here, you can fit it with mass, star formation rate, and then a T value. If you choose one T value, that'll be T50. This is when the galaxy formed half its mass. You can add additional T values, and that'll create even more complex star formation histories. For now, I'm just using the single one because we're really in the proof of concept of this methodology. And in fact, when I use this for my stellar population fitting, I'm only using two parameters. That's T50 and specific star formation rate, because from my fitting code, I get mass for free. And so, yeah, that just makes it easier to do the star formation histories for this. And here are the star formation history fits for each of the different regions. They're not perfect, but they are pretty good. Star formation rates are pretty close. The shapes are, sort of there. There's a lot of error, and we're still working on this. I think part of the reason it's not great, it's not perfect, or it's not ever going to be perfect, but I think some of the ways we can improve this is just to improve the priors. That's actually a really important thing for this fitting, are the priors. So yeah, we need to look more at the priors that we're using. And also, remember that we're doing SED fitting where the SEDs are contaminated by other SEDs. So I don't know how much that's actually going into this and causing some of these issues. And that's something we're going to have to figure out from the testing. These are for the the older parts of the galaxies. And then when we look at these star forming parts of the galaxies, it actually fits it really, really well. But yeah, so, you know, what are the use cases for this kind of SED fitting? Well, remember, again, we're going to do this not on a few galaxies, on hundreds of galaxies. And so for hundreds of galaxies, we will get dust maps, star formation history maps, and stellar metallicity maps. Now, I haven't really talked about stellar metallicity. And that's because the fits that I use to generate my models were done with photometry, where it was just assumed a solar stellar metallicity. So each one of the pixels here had a solar stellar metallicity. So there's no variation in metallicity in these models. It will say that the fits I end up getting are, because I do fit for metallicity in my fitting, I do find a solar stellar metallicity. But without the variation, it's really tough to say, you know, that's impressive. And really, it's not a question of can we fit stellar metallicity, because I've already shown that in previous work, you can use grism spectra to fit stellar metallicity. It's a question of how well can you fit the stellar metallicity, how well can you actually constrain it. So that's something to do, some future work to do, is to figure out how to incorporate metallicity in these simulated data and try to derive it. Another thing you can do with these are focus on specific parts of galaxies, right? So like I showed in the galaxy just talked about, right? We had the star forming region, we had the two different cores. So you can focus in specifically on those parts of the galaxies. Potentially, you can even focus in on AGN, right? If you just have an interesting portion of the galaxy, we can generate a segmentation map that focuses in on there, and you can fit specifically that part of the galaxy. I mean, you have to fit everything else too, but you can focus in on specific parts, and that's an interesting thing we can do there. And lastly, we will generate better emission line maps. Like I had mentioned before, the way you generate these emission line maps is you fit the continuum and then you remove it, essentially. Well, if you have a gradient, right, if your continuum changes across the galaxy, that won't be accounted for, because currently you're just using one SED to fit it. And so that variation will just go into your emission line maps, and your emission line maps may be broader or smaller than you expect. But because we can account for variations in the continuum, we can create better emission line maps using this method. So what about future work? Because as I mentioned, this method is still super early on. Well, one of the things we need to figure out when it comes to segmenting the galaxy, because that's really an extremely important part of this process, we sort of need to figure out, is there a signal to noise limit, you know, with each one of these regions? That is almost certainly true. What is that signal to noise limit? We don't know. Something else is there a limit to how large or how small really these regions can be? As I had mentioned, maybe we can use this to do AGN. And if the AGN is just, you know, a handful, you know, couple 4 pixels in the center of your galaxy, can you actually reliably get fits from just a little 4 pixel region? So that's something we need to figure out in our testing. We need to look at our priors, because the priors are going to affect the SED fitting and the runtime, and of course, and how reliably we can get these fits. We are looking into machine learning methods to better sample the priors. And of course, last, we need to test on real NIRISS data. That'll be the last step. And we're just waiting for that data to come in. And hopefully by the time it actually comes in, a lot of these other things have been smoothed over, and we can get some really nice fits. So came in a little short in time, but that's fine. So I'll go ahead and summarize what I talked about. So with grism data, you get large samples of spatially resolved spectra. And in order to take advantage of the spatially resolved nature of this, I've developed a a method to fit multiple regions within galaxies using forward modeling to derive spatially resolved SED fits with grism data. So thank you all again for coming, and I'll take any questions.
Thank you so much, Vince. That was fascinating. It's amazing what you can do with grism data. It's just so complex, and the spatial aspect of it just really adds a lot to our understanding of these high redshift galaxies. So I'm excited to see where this research goes. So before any questions that I have, I'd like to open up the floor to anybody who has a question. Please raise your hand. You can write a question out, whatever you feel like. I'll give you a couple moments to do that. Oh, we already have Jasleen Mitharu. Please unmute yourself and ask your question.
Hi, Vince. Just wanted to say really good talk. It was incredible what you're doing with the modeling. It's so impressive. I wanted to ask, so the galaxy you showed, that you said it has 2 cores, and that's causing challenges in the fitting. I was wondering, because you want to automate this whole process, in your process, are you going to include some sort of prescription to deal with possible mergers and, separate those, and so that you deal with those differently versus those that have a single core? Is that something you have to develop, or are you going to use someone else's code to do that first?
That would hopefully be part of the code we develop. Here's some of the properties of this galaxy. If we have, if we've done the spatially resolved fits with photometry, we'll have some of these. And so when we go to segment it, we may have to use some of these, some things like age or, specific star formation rate. And hopefully those will help us, separate those two. We would like to automate it. I do think in the end, we will have to go in and check every single segmentation map. It's fine. And there's hundreds of them, but that'll take a day of just sitting there and scrolling through images. That just might have to happen.
Thank you, Jasleen. I see Joel. Joel, please ask your question.
Hey, Vince. Yeah, very enjoyable talk. I really appreciate the complexity of the work that you're trying to do. Yeah, I have a few questions, I guess, related to all of the methodology. But I'll maybe just start with 1 or 2 and then hand the mic back over to someone else. So the first question is just to make sure I understand, is this morphological, I think you call it morphological self-broadening, or maybe you also use the term self-contamination. This is all just due to, on the exposures that you get from HST or from JWST, you're mapping different spatial parts of the galaxy onto a single wavelength axis. Is that correct?
Yes, I think so.
Okay. So what about the internal kinematics of say the stars or gas in the galaxy as well? Does that also contribute to the broadening? I assume it would be on a much smaller scale, but do you see any kind of issues popping up related to that?
So when it comes to velocities, the grism spectra is low resolution, are in the low hundreds. So we're ignoring it because we can't really measure velocities with that lower resolution. I have seen talks from people who actually do claim that they can do it. I've never seen anything there. So for the most part, if we see broadening, it's going to come from the morphology. Just because of how low resolution this data is.
Okay. So the next question is, now I think you made this clear that this occurs with Gabe Bremer's Grizzly code, that the use of models themselves to try and unwind this broadening that happens when you collapse the data down to just a single spectrum. Maybe this 2D method as well, though. I believe you're using stellar population models as well to grapple with that. And I think maybe some of the slides that you did showed, like where you were looking at the residuals of the modeling, right? You do get some, right? So I'm wondering, what kind of systematics might creep in to extracting the spectra of these different regions, or just of the full, like a single spectrum of the whole galaxy in the case of Grizzly. What kind of systematics might creep in because of that dependence on the models?
I think I understand your question. So I think the biggest systematic we have to worry about is actually just contamination from other sources, and how well that is actually removed. And this is something, if you are looking to work with grism data, you should absolutely check, each dispersion of it, because as well, you can't always remove all the contamination. And I've seen plenty of spectra where there's just residual contamination, like half the galaxy, which is the most frustrating part, is that you'll have residual contamination left there and it's just not removed. And if you don't know that you fit, you're just going to get this weird shape there. There's also things like the zeroth order dispersions can create things that look like emission lines in the spectra, which again aren't really there. So it's really modeling, it's how well you can model that contamination. And Grizzly does a good job, but you still definitely should check things by eye.
Mm-hmm. I guess just like maybe like to make a really contrived example of what I'm thinking about is like say you had a stellar pop model that for whatever reason just doesn't reproduce, say, the magnesium triplet in a galaxy's in a galaxy spectrum very well. How will, say, the results of this kind of forward modeling suffer in that kind of example, right? Like, I mean, for instance, I mean, are you only getting out like the model, like a model reconstruction of the data,
Yes.
like you're not actually getting the actual raw spectrum of the galaxy or of different regions in the galaxy, so that you can maybe take that and model it with something else or whatever, right? Like, or you can just sort of see that.
Yeah, for something like that, we would need to look at something called a template error function. So yeah, that would essentially, what you do there is essentially what I'm showing you here, where you take your best fit model, you find the residuals, and that's basically telling you where, and something that actually fits well. But it shows you where the models lack in reproducing the data. So if, for instance, this magnesium triplet, if that was pretty consistent, you would do this with a large sample of galaxies. Mm-hmm. But if you found that you just consistently were underrepresenting that, you would model that as an error function. And so that would just go into there. So it would downweigh that part of the spectra when you fit, essentially. Mm-hmm. I've done that kind of thing in the past for 1D spectrum.
Yeah. Still, yeah, like this is in spite of all my internal uncertainties about all this, or just I do appreciate how challenging it is. It's really very cool work that you're doing. So yeah, thank you for sharing it with us.
Yeah, thanks.
We have a question from Karthik. In case you don't want to read it in the chat, I'll read it out loud for anybody. Hi, Vince. That was a really great talk. How do you think of the relation between segments for grism fitting versus physically distinct stellar populations, i.e. the bulge, disk, star-forming knots, etc.? Do you think parametric models, plus maybe a few extra segments, could help keep things manageable in terms of fitting / number of segments?
Yeah, that's something that I've thought about, because the way I'm doing this, I'm using a code called Dynasty, and that can, it's not MCMC, but it's along the same lines, and it can take a long time to fit. It's not something like a grid or something, as fast as like dense basis, but that could be something we turn to if we really want to, if we have for instance, a big long arc that's, we want to fit, we might turn to something like that to make everything more manageable. Yeah, that's just something we might end up turning to.
That could be interesting. I'm actually curious about this. Karthik, do you have ideas of how this could be implemented? I'm just curious about this.
So the way I thought of it was almost you do it in two steps, right? Like you do the morphological modeling with near-cam or like just imaging first, and if you actually have like a disk profile or something, so you have like multiple sursics that you're fitting for these populations, like, and then they don't have to be like thick edged, like sort of like in your current model, all the edges have to be very sharp. And so you could relax that a bit. And
you were just saying.
And so you have like a couple of like these background models, and then above that, you take the residual, and then whatever's left, you do the segmentation on that.
Yeah, that should be doable to build the models. That, yeah, I could totally see doing something like that.
Yeah.
No, this is
very
really
interesting.
cool.
Yeah, extremely.
Thanks,
Do we have any other? Yeah. Do we have any other questions from audience members? While people think of things, Vince. So I know that you're developing these models for working with NIRISS models. Can you tell us a little bit about the data that you'll be applying this to from JWST?
Yeah, so I'm part of Canucks, and so this will be using the Canucks data. This the 3 filters I'm showing you here are the 3 filters we will be using. And yeah, I'm just hopefully going to use this on some, lens galaxies and see what kind of cool things we can get from these big arcs, things like that, and just all sorts of different galaxies. There's multiple applications of this that we can look at, and yeah, what I'm showing you right now is for NIRISS, but of course this methodology can be applied to any grism. So yeah.
Okay, so this could be used then for 3D for the HST grism then, right?
Certainly, yeah. The concern, with some of the other ones may be what I mentioned with signal to noise. You just need, I don't know what the signal to noise limit of this method is. And so for some of the other ones, we may have to make larger segments to account for that, but maybe not. We don't know yet. But yeah. I mean, it's exciting because I'm talking about doing this with hundreds of galaxies. But when we talk about things like Roman, we'll be talking about doing this for thousands of galaxies.
Very nice. Oh, and I see another comment from Marcin. You may want to say a few words about what Canucks is. Some people here may not know.
Yeah, so with Canucks, we're going to get, I don't know how many clusters, but we're going to get some NIRISS data for several clusters. So yeah, we'll have lensed galaxies, and we'll have the NIRISS data of that. I don't know, Marcin, if you want to give a much better explanation of what Canucks is. But yeah, we're going to get, Marcin, you should give the better explanation.
Yeah, just you got it right. It's NIRISS data on 5 clusters. Total of 200 hours of NIRISS guaranteed time observations, plus also some imaging as well. But the nutshell is that it's a very deep NIRISS slitless grism program on James Webb that's going to start observing in a couple of months.
It's very exciting, particularly of galaxy clusters for me. But let's see. Any other questions before from audience members before I start getting into it with Vince? Please. Okay, so so have you actually tried doing a model like this for, say, a lensed high redshift galaxy? Because so far we've seen this with an unlensed galaxy merger. So just like a simple case of putting a galaxy through a lens model, maybe something that we know is already in one of the clusters that's being studied. Has this been looked at all? I'm curious about how lensing affects the grism dispersion.
No, I've not tried that. There has been work done similar to what you just said. Kate Whitaker, I think, has looked at grism images of arcs. And so you can see what it does there. I mean, we're talking about these big, long things. The grism images are huge. Yeah, that is definitely something we could try, simulating arcs and seeing, how are we going to segment that, especially by multiple images. That'll be an interesting way to do it. Not try.
Yeah, it would be very interesting. I was just curious about how that would be done. Anyway, we have only 5 more minutes if people want to take it. Otherwise, we can adjourn if there are no more questions. But let's give a couple of seconds. For now, I just want to thank Vince so much for talking to us about this fascinating modeling project. So if everybody wants to give Vince a virtual round of applause, as some currently are.
Thank you.
Thank you so much.
Yeah, thank you all for having me.
Yeah, very, very interesting work. And thank you, everybody.
Thanks, everyone.
Our next, we'll send out an announcement for our next talk in about a month.
Thanks, Vince.
Thanks.
I'll end the recording.